Okay, this leads to my big question. If the network is constantly mixing these features, like you said, mixing sound waves on the same radio channel, doesn't that cause massive interference?
Yes,
I mean, if the Apple code and the Mountain code share a neuron and I try to activate the Apple concept, doesn't the Mountain concept start interfering and just muddying the whole calculation?
it absolutely does cause interference, and this is where the efficiency calculation gets really nuanced. The cost of compression is interference, but the network is highly specialized to clean up that mess.
The ability to manage this interference is why it all works.
It's the only reason it works.
So how does it manage it? This feels like a crucial technical point that's often just skipped in high-level summaries. How does the network filter out the interference?
The secret lies in the nonlinear activation functions, specifically something called ReLU or its variants like JLU, which are applied right after the weighted sum in the neuron.
ReLU, rectified linear unit.
That's the one. And you can think of these functions as being highly effective cleanup crews.
Okay, explain how ReLU works in this context.
So standard computation in a network involves matrices and vectors. When features overlap, the signal for the feature you want might be strongly positive, but the interference signal from the feature you don't want might be weakly negative.
It's pulling in the wrong direction.
Just slightly, yeah. ReLU works by a very simple rule. It sets all negative inputs to 0. It just says, if the combined signal is less than 0, I discard it completely.
So if the Apple feature vector is pointing strongly in one direction and the Mountain feature is interfering by trying to pull the signal slightly in the negative direction, ReLU essentially just snips off that negative interference.
Exactly. It enforces a critical form of sparsity after the initial compression. It filters out the noise and only allows the strong, positive, intended signal to pass through to the next layer.
Wow.
This mechanism is key to why networks can handle these highly compressed, overlapping codes. The ReLU operation is constantly clearing the channel, filtering out the crosstalk caused by superposition.
So the compression strategy is only viable because the subsequent layers, powered by ReLU, are designed to aggressively discard irrelevant negative noise. That's a beautiful system.
It is. And this compression is most effective under one key condition:
Which is?
when the features are sparse. This is the mathematical reason the network is willing to accept the risk of all this overlap.
Let's define sparse clearly again. It just means rare, right? Infrequently encountered features?
Correct. The network is essentially taking a massive statistical gamble. It knows it needs to learn the Apple feature and the Mountain feature, but they are relatively rare in the corpus, and, crucially, they are statistically unlikely to be needed at the exact same moment in time.
It's betting that the risk of feature A and feature B both lighting up at once and causing catastrophic interference is just very, very low.
Exactly. If you have 10,000 rare features and you only have 1,000 neurons, you can maybe pack 10 features per neuron, just assuming that only 1 or 2 of those features will ever be relevant in any single input.
And if the features were dense, if they were required all the time.
Superposition would fail instantly. It would be constant, unavoidable interference, a total mess.